Yes, in the last video, we completed a modeling of tank using ETABS software. So, what are the inputs that I have used for modeling are, so tank size 10 meter by 8 meter, total height of the tank 5 meter, height of fluid 5 meter, grade of concrete M30, grade of steel Fe 500, thickness of wall 350, thickness of base slab 500 mm, and we used mesh size 0.25 meter for walls. For base slab also we used 0.25 meter. So for walls we used physical meshing. For base slab we meshed it as auto mesh. Clear? So today we will see how to calculate the loads. So first type is dead load. So first type of load is dead load. So dead load is nothing but self weight. So self weight, it is automatically calculated by the ETABS software itself based on the sizes. So no need to calculate and assign the dead loads again. Okay. So next, live load. So if you see the tank model, so there is no top slab. So because there is no top slab, no live load. There will be no live load. So here it is. No live load. Next, we will calculate water pressure. Water pressure on vertical wall. So this is first, second, and this will be third one. So third one is water pressure on vertical wall. So height of wall is 5 meter. So we assume the liquid is filled till the top. Okay. So if this is your elevation of the tank, so bottom is fixed. So this is your elevation of the tank. So here this is bottom of the tank, and this will be top of the tank. So total height of the tank. So total this height of the tank, it is 5 meter. So here Z coordinate is 0 and Z coordinate is 5. So to check this, you go to ETABS. See here at the bottom, you select this joint, you right click. So here in geometry, so global Z, it is 0. Okay. So at the top level, So you select this joint. So geometry, global Z, it is 5 meter. So height of the tank is 5. Okay. The water pressure on vertical wall will be a triangular distribution. So it will be like this, triangular. So at the top it is 0 and at the bottom it is minus 50 kilonewton meter square. So why it is minus 50? See here density of water multiplied by height of the tank. So density of water is 10 and height of the water is 5 meter. So 10 into 5, 50 kilonewton per meter square. So if you observe your ETABS model, so local axis 3 for walls, this local axis 3 will be for walls. So this local axis 3, blue color axis, which is pointing inwards. So go to plan. So for all the walls, your local axis 3 is pointing inwards. So this is local axis 3. For all the walls, it is pointing inwards. You are going to apply the water pressure load in opposite direction. You are going to apply the water pressure in opposite direction, opposite of local axis 3 for all the walls. For all the walls, it is opposite. So therefore, your pressure value will be minus 50. So here it is minus 50. So it is very difficult to assign it as uniform pressure or uniform shell loads. In ETABS, you have an option called non-uniform shell loads. So this triangular distribution can be applied on your vertical walls as non-uniform shell loads. Okay. So how to assign these loads? See, in ETABS, if you open ETABS, so you go to assign shell loads non-uniform. You have this equation, load at point xyz equals ax by plus cz plus d. X, Y, Z and Z are in the global coordinate system. So okay, I will use same equation. So equation is ax plus by plus cz plus d equals your pressure. So here x is 0, y is 0 because your pressure distribution is along z direction. So your remaining equation is cz plus d equals p. Okay. So here you have the two boundary conditions. First condition is, when when Z equals 5, Z equals 5, your P is 0 kilonewton per meter square. This is at the top of tank. Okay, this is first condition. So second condition is when Z equals 0, your pressure will be minus 50 kilonewton per meter square. So this is at the bottom. So you know the equation Cz plus D equals P. So in this equation, so I'll call this as equation number 1. So in this equation, I will use condition 1. So that is C, so Z equals 5 plus D, so pressure will be 0. So I will put this condition. If I use the second condition in the same equation, so C into Z0 plus D equals, it is minus 50. So you have two equations. If you solve these two equations, you will get C and D values. You will get C and D values. So your first equation is C into 5 . So your first equation is C into 5 plus D equals 0 and C into 0 plus D equals minus 50. Okay, correct. So solve for C and D. So your C value is 10 and D value is minus 50. See here. So here C value is 10 and D value is minus 50. Okay. So these constants are for this water pressure on vertical wall. So C equals 10, D equals minus 50. So I will show you how to assign these loads on ETABS software. So anyway, dead load will be calculated automatically by the software. So no top slab. So therefore no live load. So we need to assign this water pressure on vertical walls in ETABS software. So first you open your ETABS software. So select all the walls. Okay. So before that you need to create load cases. So first you go to define load patterns. So by default there will be a two load patterns. So one is dead and another one is live. So in case of self weight multiplier, you put 1 in the case of dead load, 0 in the case of live load. If you put one other than the dead load case, in any other load cases other than the dead load. So your self weight will be gets duplicated. So please ensure this. So self weight multiplier should be 1 in dead, 0 in live load. Okay. So by default I have two patterns, dead, live. So next I will create water pressure. So next I will create water pressure. So in case of load, you write water pressure. So type, it is other, self weight multiplier, it should be 0. So you just click on this add new load. See here. So here you have the new load pattern called as water pressure. One is dead, live, water pressure. So first one will be dead load, live load. Okay. No need to assign dead load. It is automatically calculated by the software based on the sizes, and there is no live load because you have not modeled any top slab. You kept your water tank as open, so no live load. So next we will assign water pressure on vertical walls. So I will go to first elevation. See here, this is your tank. If you see here, from inside it is completely filled with water. So on all the four walls you have triangular distribution like this. On all the four walls your water pressure distribution will be triangular. So at the top it is 0, at the bottom it is 50 kilonewton per meter square from inside. Why at the time of calculation I have taken this as minus 50? Because if you see the local axis 3, if you see the local axis 3, so this, see here, this local axis 3, it is pointing inwards. You are applying water pressure opposite to this local axis 3. So it is taken as minus 50. Clear? Okay. So how to assign this load? You select all the walls. You select all the walls. You select all the walls. You go to assign shell loads, non-uniform. In case of water pressure, your load pattern should be, name should be water pressure. So you are which means you are applying water pressure, water load. In which direction? Your direction should be local 3. So A value is 0, B value is 0, your C value, see here, C value is 10, D value is minus 50. So C value is 10, D value is minus 50. So you click on apply, OK. So go to display undeformed shape. So if you click on any shell object, so you click mouse right button. So in case of load, see here, you have the load pattern, in which direction it is local 3 and it is applied as non-uniform. So your A value is 0, B value is 0, C value is 10 and D value is minus 50. It will not show you the arrow mark physically. So it is shown in terms of these constants. In SAP 2000, you have the beautiful option. The water pressure can be visible like arrow mark. You can easily identify on what direction it is acting. Okay. So we completed this water pressure on vertical wall, live load, dead load. Next, we shall calculate. So fourth, soil pressure. Soil pressure on vertical walls. So in the beginning, in the question, we assumed soil pressure is 1 meter below the top level of wall, or your tank is partially underground tank. See here. So inside tank, your tank is completely filled with water. So you have taken pressure distribution from top of the tank to bottom. You taken pressure distribution diagram as from this 0, here it is 50, here Z value is 5 meter and here Z value is 0. You taken complete area, or the water is entirely filled, the tank is full. But in case of soil pressure, so you have soil pressure 1 meter below the top level of wall. So which means your soil pressure is acting like this from outside. So it is acting on these walls like this, on all the 4 walls. On all the 4 walls, it is acting like this, because total height of the tank is 5. Total height of the tank is 5 meter. Your soil pressure is this much only, 4 meter. So here you need to leave this 1 meter. So your mesh size is 0.25 meter. So each this square size is 0.25 meter. So for 1 meter length, you need to leave 4 elements from the top. So 2, 3, 4. So soil pressure is acting on these areas only. So this much of wall is subjected to soil pressure from outside. So it may vary case to case. In case of assignment questions, we received, some students have received 1 meter, some received 1.5. So you have to plan accordingly. See here, I will repeat it once again. So your water pressure is from full, but whereas your soil pressure is 1 meter below the top of tank. Okay, on all the 4 walls. So how to calculate? First we shall see the calculation, then we will assign it. So soil pressure on vertical walls. So what they have mentioned, it is 1 meter below, 1 meter below the top level of wall. Okay. See here, this is the elevation of the tank. Bottom is fixed, top is free. So total height of the tank, it is 5 meter. So your soil pressure is only this much, 4 meter. So your local axis 3, your local axis 3. So it is acting inwards. Okay. So it is inside the tank. So this is your local axis 3. This is towards inside. Your soil pressure is acting from outside like this. It is also a triangular distribution. So here at the bottom Z value is 0. At this location Z value is 4. So at this level your soil pressure is 0 kilonewton meter square. But at this level, so your soil pressure is Ka gamma S into H. Okay. So Ka is again, it is a constant. So Ka, it is earth pressure coefficient. So to get the Ka value, so you need to refer IS 3370 part 2. So year 2021, clause 4 point, clause 4.2.6. So let me open the code. So it is part 2. So 4.6.2. sorry, 4.2.6. Yes. So this 4.2.6. Okay. See here. Earth pressure coefficient should be in between the values at rest and at active state, but shall not be less than 0.5 in any case. So your coefficient of earth pressure Ka, it should not be less than 0.5 in any case. Okay. So this is as per IS 3370 part 2 2021. So your Ka value is 0.5 here, and your gamma S. So your gamma S is unit weight of dry soil or unsaturated soil. So it can be taken as 18 kilonewton per meter cube. So at the bottom pressure will be 0.5 into 18 into, so height will be 4, because so your soil pressure distribution will be up to 4-meter height. So 0.5 into 18 into 4. So it is 36 kilonewton per meter square. Again you need to calculate C and D values. So what are the conditions that I can write? So first condition is when Z equals 0, our pressure, soil pressure will be 36 kilonewton per meter square. So when Z equals 4, your soil pressure is 0 kilonewton per meter square. See here, your soil pressure is acting along the local axis 3. So here it is plus 36. While your water pressure is acting opposite to your local axis 3. So there I have considered it as minus. So here it is plus only. Okay. So you know the equation. So you know the equation. Ax plus by plus cz plus d equals pressure. So here x, y are 0. So your equation will be cz plus d equals p. So if I use first equation, first condition, so your equation will becomes cz0 plus d equals 36. If I use second condition here, you will get C Z value 4 plus D equals 0. So if you solve these two equations, you will get C and D values. Okay. So your first equation is C into 0 plus D equals 36, and your second equation is C into 4 plus D equals 0. So solve for C and D. So your C is -9 and D is 36 here. So your C value is -9 and D value is 36. So these are the constants for this case. So C -9, D 36. Okay. So now we shall see how to apply these constants. So you should be very careful while assigning the soil pressure on vertical walls, because you have to unselect wall elements which are 1 meter from top while assigning the earth pressure. Okay. So you go to ETABS. So first you go to define load pattern. You create another load pattern called soil pressure or earth pressure, both are same. Soil pressure, soil pressure. In case of type, you select other self-weight multiplier. It should be 0. Add new load case. See here, you have dead now live water pressure, soil pressure. You just click on OK. So you go to any of the elevation. So you need to select wall elements which are at 4 meter from the bottom. So which means you need to unselect these 4 elements, 1, 2, 3, 4. So I will select only these elements. So this is elevation A. You go to next elevation, elevation B. So you leave these 4 shells, 1, 2, 3, 4. You select this. You go to next elevation 1. You leave this 1, 2, 3, 4. So next elevation 2. You leave this 1, 2, 3, 4. You select only this much. Okay, you go to 3D. See here, you have selected shell elements which are at the level 0 to 4 meter only. So you go to assign shell loads non-uniform. So in case of soil pressure, local 3. So A0, B0, C value -9 and your D value is 36. You click on apply. OK. So go to display undeformed shape. You select any of the elevation. If you see the first topmost shell element, you have only water pressure. If you select the fifth element, 1, 2, 3, 4, fifth shell element, you have soil pressure, In addition to that, you have water pressure. So for water pressure, your C and D are 10 and -50. For soil pressure, C and D are -9 and 36. Clear? Okay. So this is how you can apply soil pressure on vertical walls. If in the question, if it is not mentioned, you have to take full height. Again you have to take full light. If it is 2 meter, if it is 2 meter, again you need to leave this 2 meter from the top. Okay, that's how you can plan it. So next will be, so fifth one, water pressure on base slab. Water pressure on base slab. Water pressure on base slab. See here, if you open ETABS, when the tank is filled with water, so there will be a pressure on this base slab also. There will be water pressure. There will be water pressure on this base slab also. So how it is calculated? See here, how it is calculated. See here. So it is calculated as gamma W into H. So gamma W is density of water 10. So H is your height of the tank. So it will be 50 kilonewton per meter square. So your gamma W is density. It is in kilonewton per meter cube. So your height of the tank, it is in meters, 5 meter. So if you multiply these two, so 10 kilonewton per meter cube multiplied by 5 meters. So you will get the water pressure in terms of kilonewton per meter square. Okay. So how to assign this on base slab by using ETABS software? It is very simple. So it can be assigned as uniform shell load assignment. So it is very simple. See here. So you go to ETABS. You go to ETABS. Select your base slab. See here. One shell selected. Select your base slab. Go to assign shell loads. So for which you select uniform. So it is in case of water pressure. So it is 50 and it is acting along gravity direction. You click on apply. OK. So go to display undeformed shape. You just click on this base slab. See here. You have water pressure uniform 50 kilonewton per meter square, and by mistakenly I have assigned non-uniform pressure also. So which means you have to delete that. So you select this shell, go to assign shell loads non-uniform. I think it is in case of water pressure local 3. You delete. You once again click on this slab. See here. Now it is correct. Load pattern, it is water pressure. You have only 50 kilonewton per meter square gravity direction, along gravity direction. Gravity means in a downward direction. So go to 3D. See here, water pressure. So if you select any of this element, you have soil pressure plus water pressure. Okay, it is correct. If you, while assigning the loads to shells or walls, you can hide this. You can hide this base slab also. See here. So you go to set display options. In case of floors, you uncheck this. Click on apply. Okay. So your base slab will be not visible in this current view. It will be there, but it is not visible in this case. So while assigning the shell loads, you can wall loads, you can easily select these walls. Okay. So how to bring it back? So you go to set display options, you select these floors, you click on apply. Okay. See here. This is your base slab. Again, similarly, how to hide these walls? You go to set display options, you select uncheck this walls, you click on apply. Okay. See here. You have only base slab. So these commands will be useful for assigning the loads. You can hide some elements and you can select some other elements. Okay. How to bring it back? Go to set display options. You just click on check this walls, click on apply. Okay. Okay. So we completed dead load, live load, water pressure and soil pressure. So in addition to that, there is a presence of water table. There is a presence of water table which is 2 meter below your NGL, natural ground level. Okay. So this presence of water table will cause uplift. So then there is a case of uplift. So next load calculation is uplift on base slab. Uplift on your base slab. See here. You have a tank like this. So this is not up to the scale. You have a tank like this. So height of the tank. So this total height of the tank, it is 5 meter. So you have water table which is 2 meter below your NGL. So this was your natural ground level. So NGL. which is at a distance of 1 meter. 1 meter. So below this NGL, at how much distance? At 2 meter distance, you have presence of water table. Then remaining this distance will be 2 meters. Okay. On what case uplift will be critical? So uplift forces will be critical in the case of tank is empty. If your tank is empty, you have uplift forces on your tank. So because of no counterbalancing force on the other side, so your uplift forces will cause the tank to lift up. So your tank may lift up. Okay. So your water table is 2 meter below NGL. So 2 meter below NGL. So which means this area is filled with water. On actual site, this area which is occupied by some of the water. So there is a presence of water. Okay. Again, this part of the tank occupied by this area. This much area is occupied by tank, and this will cause uplift on walls, uplift on these walls, and uplift on this base slab also. So this water table will create pressure on these walls also, and it will create pressure on this base slab also. So now you are calculating uplift on base slab. You are calculating this pressure, this uplift on base slab. So this is uplift on base slab, and this is uplift on walls. So now we will calculate uplift on base slab. So how to calculate? It is pretty simple. So it is density of water multiplied by height. So density of water is 10, and height means this height. So this is the depth of water table. So it is 2 meter. So 10 into 2. So it will be 20 kilonewton per meter square. And it is acting opposite to gravity. And it is acting opposite to gravity direction. So we will see how to assign this. So you go to ETABS, you select only base slab. You select only the base slab. Go to assign shell loads. Oh, sorry. So before that, you need to create a load pattern. So you go to define load pattern. So you need to create one more load pattern called uplift. uplift. So you select other, sulfate multiplier 0. You just click on this, add new load. So you have dead, live, water pressure, soil pressure, uplift. You click on OK. You select this base slab only. You go to assign shell loads uniform. In case of load pattern name, you select uplift. It is gravity, but it is opposite to gravity. Here you should type -20. If you take +20, it will be in a downward direction. If you see here, if you see this, your water will be along downward direction. Water pressure will be on base slab, it is in downward direction. So you have taken +50, whereas your uplift is, it is also in gravity direction, but it is acting in opposite. So it is -20. Okay. So load pattern name uplift, load -20, direction gravity. You click on apply. Okay. You go to display, undeformed shape. You just click your shell. You have uplift on this base slab. You have two forces or pressures. One is uplift, another one is water pressure. So water pressure is along downward direction. So which is plus. Uplift is opposite. So it is minus. You just click on OK. So next it will be next part of your load calculation is uplift on walls. So this is very interesting. So this may be seventh case. So uplift on vertical, uplift on vertical walls. Okay. I will stop it here. We will take up this in the next video, because again it is a huge calculation. You practice this much. So up to uplift on base slab. Okay. So we will take up this calculation in the next video. Uplift on vertical walls. Okay. So while discussing the uplift, what is the self weight of the tank here? What is the self weight of the tank here? Self weight of tank. How we will calculate the self weight of tank? First you need volume of water. So volume of water is 10 into 8 into 5. So you will get volume of water. So it is 400 meter cube. If you multiply the tank size, you will get volume of water. Okay. Next, base slab volume. base slab volume. So size of the base slab is 10 by 8. Thickness of base slab is 0.5. So 10 into 8 into 0.5. So it is 40. 40 meter cube. And you need volume of walls. So for which you need perimeter multiplied by thickness multiplied by height of the tank. So perimeter you will get 2 times, which means 2 walls. So 10-meter walls, 10-meter walls plus 8-meter walls, plus 8-meter walls. So total perimeter will be 36 meters. So volume of wall will be 36 into thickness of wall 0.35 into height of the wall 5. So here 36 multiplied by 0.35 multiplied by 5. So it is 63 m cube. 63 m cube. So total volume. So it will be total concrete volume. If you see here, total concrete volume. So it will be slab plus walls. So base slab it is 40. So here it is 40 plus walls 63. So it will be 63 plus 40. So it will be 103 meter cube. So 103 meter cube. So this is the total concrete volume. So if assume density of concrete as 25 kilonewton per meter cube, so then this concrete weight would be, so volume multiplied by density 25 kilonewton per meter cube. So 103 multiplied by 25. It is 2575. It is 2575 kilonewton. Okay. So this is the weight of the tank or self weight of the tank. So your self weight of the tank is self weight of tank is 2575 kilonewton. So my question is, when the tank will lift up, when the tank will lift up, see here, you calculated the self weight of the tank, it is 2575 kilonewton. Here you have the uplift on your base slab. So this plan area is 10 into 8, 10 into 8, and the density of soil, here it is submerged soil, so it is 20. So 10 into 8 into 20. So here it is 1600 kilonewton. Let me check this. 10 into 8 into 20. Yes, it is 1600 kilonewton. See here. Here the self weight of the tank is 2575 kilonewton, whereas uplift pressure on this base slab is 1600 kilonewton. In this case, will it be your tank lift up? No. So next, if not, if your self weight of tank, if your self weight of tank is less than 1600 kilonewton, so then the tank will then the tank will lift up. So in this case, it will not lift up because your self weight is more than your, what is this, uplift pressure at base. Okay, so in our case, lifting of tank is not critical. Anyway, we'll consider in the load calculation. Okay, so you practice these things. In the next video, we will take up uplift on vertical walls. We will take up this.